want to make sure the concept come across. But don't tell me, say, yeah, you think this is not a math class, but there's a math. Of course, there will be a math. There will be math, there will be physics. Okay, but trying to get your idea, it is really a quantum mechanics class involving your foundation, your previous knowledge with math and physics. All right. Okay. All right, now let's get to the fun part of it. So we started, we discussed about rotation on the plane. Now we extrapolate to the three-dimensional rotation. As you can see, the model is still a free particle rotation. On a three-dimensional system, we use a sphere. Okay. In this case, we say we will fix the radius of the sphere. So therefore, from a three-dimensional system from x, y, z, now you extrapolate to from Cartesian coordinates to spherical coordinates. You reduce your variable from x, y, z to either theta and phi. So it only depends on those two angles. Okay, now we already know from the math, the phi is from 0 to 2 pi, then around your colatitude, right? The theta is from the pole, from the one pole to the other, that's from 0 to pi. Now, how are we going to approach this problem? What you can think is, this is really a stacking of the two-dimensional rotation. So you can think about it as, if you look at this sphere, you see the slice. So each of the slice is really a rotation on the xy plane, except now you have a rotation on the xy plane intercept at different theta values. Okay, so you can think about this as really a stacking of the rotation on the plane. Now you have a different theta value from 0 to pi. Okay, now if that is clear, then we will start with the Hamiltonian operator as usual, and then we go solving for the Schrodinger equation. So today you're going to enjoy a bit of the math. You know, I like chemistry, but I also love math and physics. They are beautiful. So this, I want to go through with you guys to show how we can solve the Schrodinger equation for your wave function. Use advanced math. Use advanced the method from the math. Okay. All right. So I have a slide here. Now I will promise you, I'll post this. My lecture notes after this lecture. So in case you didn't capture all of them, I'll give it to you. I want you to enjoy the beauty of how we solve this problem. Okay, so what we said, we need to generate the Hamiltonian operator, which we already talked about this. So you have x, y, z component, right, generically. Now, because it's a free particle, so you're considering a free particle, so therefore this Hamiltonian operator, we only have the component for the kinetic energy, right? Okay. Can you, it's embarrassing, right? I need a more beef or something.
No pressure.
Okay, thank you. Alrighty. Alright. So they only have the component for the kinetic energy part. Now it's a rotation on the sphere. It's a three-dimensional component. So therefore, you will have the components in the x, y, z. Their square is really the second-order derivative with respect to the x, y, z components. Now, their square, it can be expressed in the x, y, z Cartesian coordinates or in the spherical coordinates. Now, if we know it's a fixed radius, so therefore your Hamiltonian operator can be simplified with the two variables instead of three. Okay, and then if we plug it in correspondingly with the exact expression, so that's what we're going to have. So what we have it here is now h bar squared over 2m, that del squared as we're showing here, we reduce to the component that is related with your the angle component. Okay, we said this is the Legendre operation. Now I can plug in that values. So this, right, equals to this is a really nothing fancy. All we got this is the conversion between x, y, z and the r theta phi. That's about it. Okay. All right. And I think that's where we ended from the previous lecture is come up the Hamiltonian operator motion in three-dimensional space. You have del squared, and if you write out your del squared, you cancel out because r is a constant, so you only reside in the component with the variable that is associated with your theta and phi. Did we all catch up on here? Okay, it's all good. All right, so this is your Hamiltonian operator. All right, now if we really want to simplify a little bit, what do you guys see here? The m and r squared can be simplified as the capital I, which is the moment of inertia. Okay, now what I'm going to do, now I don't think some of you guys have fancy iPads and other things. I can easily erase this guy and make it dry. Okay. All right. Now this is the Hamiltonian operator. Now what we do in the next step is plug it into the Schrödinger equation. All right. So the Schrödinger equation is the your energy operator, Hamiltonian operator, operate onto the wave function on the right side. Return your value for the energy multiplied by this wave function. Okay. Now we say the wave function using the Cartesian coordinates, you have x, y, z. Now if we switch to the spherical coordinates, and now we know we constrain set one of the variable r as a constant, so effectively we reduce the variable to only theta and phi. So here we carry the r squared, but r is really the constant, right? That's nothing fancy. Okay. All right. Any questions on this? All right. So now let's plug it in. So we're going to have this Hamiltonian operator. I'm going to take a shortcut, guys. This is your Hamiltonian operator. Let's write this. Okay, so this is your Hamiltonian operator. Now, I will operate onto the wave function. Okay, I don't want to rewrite the whole thing again. You guys all follow me, okay? So I have a Hamiltonian operator operate onto the wave function. Okay, now we're going to use the distributed property. You can think about it. I have this component operate onto the wave function, then I have this component operate onto the wave function. So I separate into. Oh, I haven't finished it yet. What do you guys think? Of course, I need to complete the Schrödinger equation. Okay, now before we keep it going, because this is what we need to solve. So you have a mathematical equation, and solving for the wave function c has two variables. How are we going to do it? That's literally a math problem, right? So I have unknowns wave function to be solved for, carry two variables. This is the mathematical equation. I know the constraint for those two variables. Now how I'm going to get a solution. I don't know how many of you guys have actually went through in your math to solving for this two variable mathematical function from one equation. But in math, we do have a trick. One trick that we say separation of variables. What does that mean? Instead of a function that depends on two variables, let's try if it is true that this is actually can be considered as a product of two functions. Each of the functions only depends on one variable. So that is the trick. Instead of directly solving for this particular math function with two variables, then mathematically you can take a shortcut. Now, if it doesn't work, you're doomed. You have to go solve as it is. If it works, then your life will be easy. So that's what I'm saying. It doesn't mean every single time, guys, we can do this. We will try. If a function depends on two variables, can we simplify, assume them as an individual function only depends on that variable? So we're going to give it a shot. Now here, this is a C wave function, depends on two variables. So can I make it into one, which one is a capital theta, just a symbol. You can use F or G, whatever you want to do, to indicate the function only depends on the variable of the theta angle here. And then other function, we use a capital phi to indicate, name that function that only depends on the phi variables. You guys follow me okay? Because we need to solve for that equation. Okay, so in that case, then if I look at this equation for the Schrödinger equation, what can I put in, guys? This will be a product of two functions. All right, now then instead of C, this will be a product of two. Then on this end, I'm just plugging in, take advantage of try to use a separation of the variables. Okay, there's really nothing fancy. Now, you guys have to try the separation variable, right? What is the trick of this? We want to make sure this can be separated each independent function, and then through the expression, once we try the separation variable for the function and we play into the expression, the trick afterwards is to separate all the terms with one variable plus the terms with the other variable. Okay, that is the trick. All right, okay, where are we? So now let's see if we can solve this. Now we have an operation. We have an operation of this component. So I will write out this for you guys. So what I'm having here, it's a constant. I don't have to do anything. H bar squared over 2i. Then when I have a component, this is just a multiplication of 1 over sine squared. But that is an operation, right? That operation operate onto the wave function. You have an operation here operating onto your wave function because your number 20 operator right now have two terms right here. So let's separate those two. So then I have the component with the variable of phi squared, but operate onto the function. So what is our function right here? Is the only small. So what I have is, I have the component and I have Hamiltonian operator operate onto the wave function. Now I try the separation variables. So there's an operation, second order derivative onto the wave function. Then I have this first order derivative with respect to the theta onto the wave function. And the wave function is a product of the two functions that only depends on one variable. Is that all clear? Okay, now I'm going slowly because I really want you guys to enjoy the beauty of this. Okay, now what can we do? Alright, now, what do you guys think about this part? This is the second order derivative with respect to variable of phi. Now, what do you guys think about the function of the theta related with theta angle?
Will be treated as constant.
Would that be treated as a constant, guys?
Yeah.
Yes, very good. Okay, so if we treat it as a constant, let me erase this. What we can have is, I'm only thinking about this part, then I can take it out from the derivative, and can we put it in? Can we put it here? All right. Now how about this part? Alright. Guys, I promise I'll post the lecture notes because I know if I'm waiting for you guys to finish it. I have time. I want to see you guys for one time, but I don't know the next class will be available. Because I don't want to rewrite this whole thing on the Friday class. Okay, so let's keep going. So how about this part? This is your derivative with respect to the variable of theta angle. So your phi function only depends on the phi variable. So then you can consider this will be constant with respect to your operation of the theta. You guys agree? Then I can take this out of the integral. Consider this will be a constant. And then I can think about it how far I can take. This is a multiplication, doesn't matter. Again, derivative to the theta, doesn't matter, so I can leave it all the way off here. Okay, now I said the trick for you to do the separation variable is you'll be able to plug into your expression. Has terms, has parts of your section, only depends on one variable, has the other part only depends on the other variables. So let's try out it here. Look at this term here. This part, right? This is with respect to the variable of phi. We want to have this part of the expression only has the variable of phi, okay? And then what we want to do is, from this part, you have the derivative with respect to theta. To make the separation variable trick work, you want to do something, if you can, to only depends on the theta part. Now what should we do? Now in that regard, this has a variable of phi. We only want to keep it as variable of phi. What do we need to do? We need to get rid of anything related with theta. How about this here? We need to get rid of anything related with phi. Very good. Now what should we do to get rid of the theta component here? I need to divide it by get rid of the theta function in the numerator. In order to get rid of that, I have to divide this expression by the theta function. True?
Yes.
So what else? I have this sine theta in the denominator. So what do I need to do? in order for this to only include the phi part, I need to multiply by this term. Okay, now how about this one? It carries the phi function. So therefore, to get out of this, in the numerator, I have to divide this whole function by the phi function, right? What else? What else? That's it. Very, very good. Great job, guys. Now I have to consider both this component and this component. So what do I need to do? Is I need to multiply if I multiply the above expression by this term, I will get what I want. Do you guys agree with that one? Okay, now let's give it a shot. What would it remain? If I multiply this term with the first part with this term right here, what do I have? So I will banish the theta, banish the sine theta squared. What do I have? Okay, excellent. Okay, now how about this second term here? Then if I multiply this term by this expression, what do I have? So this will be done, right? Remains with what? The function of theta. What do I have? I shouldn't erase the whole thing. What do we erase, guys?
That was phi function.
Does that make sense? Yeah. Yeah. Okay, very good. All right. Okay, now what happened to this side? We're not done yet. We only did the one positive expression. It's an equal sign. What happened here?
You can get rid of both.
So I don't have
E sine squared.
any of this, right? And then what do I have here? So basically, what we explore is the methodology about the separation of variables. You evaluate your expression. Since you're trying to do a separation variable, so therefore after you do the function, then you want to be sure, can I manipulate the expression to separate it into the terms only have one variables. Okay, now I think that we accomplished this term only have sine phi variables, this term only have theta variables, and this term only have theta variables. So I think this would work. Well, I tried. Okay. Now, what I want to do is, I do not want to have a coefficient in front of this expression. Just to make it simple. Then what I need to do is, I'm going to multiply by a negative 2i h bar squared. If I multiply this above expression by 2i over h bar squared, I'll make the left side of that coefficient become 1, right? Right?
Yeah.
Okay. All right. so it's easy for me to become 1, I just erase this whole thing. So then here will be the negative 2I over h bar squared. It's an expression, you have to multiply both left and right side. You guys all following me, okay? Okay, we're getting closer, I promise you. All right, now I want to make everything to be 0 on one side. So I'm going to move the e to the left side of the expression. Okay, and then what do we have? Well, maybe I'll just leave it here for a minute. So let's just simplify this. So what I have in here is the e 2I negative h bar. So I can combine this. Okay, so I can combine this. Okay. All good? Okay. All right. And then move to the left side. Any questions on this? Okay. All right. Now, don't ask me, it's a mathematics. A lot of time we just don't want to write a lot of things. We can substitute this whole thing with a simpler notation. We can make this we can substitute. It's like we did for the rotational motion. Instead of expression in terms of x variable, we use a y variable just to make this expression a little bit simpler. But if you wish you want to carry that's fine too. There's really no problem at all. So basically, we want to make this expression to be looking simpler. So we can substitute this 2I moment of inertia times the energy of this three-dimensional rotational system over the h bar using a epsilon to represent. Okay, it's really nothing fancy. It's just a substitution. So I can erase this and say this is just a constant equals to 0. Any questions on that? All right, now let's take a look at this. So we will have this term only depend the variable of phi, only depends on the variable of phi. And we have this two of them only depends on the variable of theta. So that's successful. Can you imagine? How can you have a term with a variable of one variable plus a term with the other variable and give you a constant 0?
If they're equal each other.
So that's the
Opposite
trick
of
of
each
the
other.
separation of variable, right? So you separate into those variable each independent term. Now you have to think about it, how I'm going to take it further. First of all, they no longer can be variable anymore. Because a variable plus some data equal to a variable. To make that to be true, what has to be true? What has to be true? For this expression to be true, what has to be true, guys? This cannot be a variable anymore. This has to be equal to a particular constant. And this also has to be a constant. Furthermore, let's say this is equal to a constant A, is equal to a constant B. What other has to be true?
A minus or A plus B equals 0.
Yes. Those two constants has to be, add them up, has to be equal to 0. So the constant A has to be a negative of 1. Constant B. So effectively what you have is one mathematical equation. Now you can separate it into two equations. Each one of them depends only on one variable. And that is the trick for the separation variables. Okay, so basically now, based on that idea, we can separate those. Right. And the second one, okay, that's the main gist of this separation of variable. Okay, that's what we get used to it. Because if you have two variables, mathematically, what do? We have two equations solving for two variables. We are very good at doing that, and we achieve that. So this particular expression only depends on the variable phi. This particular expression only depends on the variable of theta. Two equations solving for two variable functions, we can do this. Now, in order to really solve for this, what do we need to know?
Constant A.
We need to know what this is. We need to know what this is. If we know what this is, we are golden right now. Okay. Now, if we evaluate this a bit further, do you guys think this expression look familiar for you? So the rotation on the two-dimensional xy plane with a fixed radius only depends on the phi variables. Okay, if I may remind you guys, about our Hamiltonian operator, the Schrodinger equation for the rotational of the two-dimensional system with a fixed radius, as I'm showing here. Did you guys see the Hamiltonian operator, which only depends on the phi variable equal to the negative h bar squared over 2I, second order derivative with respect to the rotational inner angle. If you plug into the Schrodinger equation, now what you see here, the derivative for the wave function second order with respect to the angle, second order, what do we have it? Right, so if I write it out here, so you have this is your Schrodinger equation for the rotational motion in a two-dimensional system. Okay, now I know it's very far. What do we have it on the other end? If I divide this expression by the wave function, and move the constant, make this constant to be 1. So what do I have? So this is from the rotational on the two-dimension Schrodinger equation. I divide this expression by the wave function on both sides. That's why you have 1 over the wave function. and your second order derivative with respect to this, and that is what you have. Are you guys going to be okay? No. This is our Schrodinger equation for rotation on the sphere, on the plane, right? So I just did some manipulation. Which part you guys? Which part is the issue right now? No issue. Okay. Now, this is a rotation on the xy plane. You are Schrodinger equation. You divide this expression by the wave function. That's why it vanished to 1 here. You multiply the constant from the whole expression. That's what we have it here. All right. Now, what is the energy expression for rotation on two-dimensional system? That equals to n squared h bar squared over 2I. We solve for this, right? The energy for rotation on a two-dimensional system equals to the quantum number squared h bar squared over 2I. Now, if I plug it in here, what do I have? Plug in the energy here. Yep. What do I see? I hope you guys know this is really the Schrodinger equation for the rotational motion. All we did is divide the whole thing by the wave function and multiply by the negative 2I over h bar squared for the whole expression. Now what do we have in here? 2I, h bar got cancelled out. What remains for the constant? If I rewrite the Schrodinger equation for the rotation on the plane, in terms of the constant on one end, it is equal to the negative m7l squared. Now take a look at guys here. That's exactly what you have. For this first part of the separation variable here, you literally have the exact expression for the rotational plane, rotational motion on the xy plane. Like 1 over the wave function, although we named this phi as the wave function, but the same. And then second order derivative with respect to the angle equal to the constant. Now guys, can you tell me what this constant is supposed to be?
ml squared.
Huh?